Yeah. So, good morning, everyone. You can let me know whether you can hear me clearly. That would be useful.
Yes.
Yeah, super. And a few of you have asked about live transcription. That's probably not a very good idea. The system, because of different accents, I speak Kenyan English, it writes the wrong things most of the time. So please just listen to me. And yeah, most of the stuff I say, I also write it down. So it's better to listen carefully and write. And if there are any issues, ask through the chat, or just turn on your mic and ask if something is unclear. So live transcription is probably not very useful for me for this particular lecture. So sorry that it's an online meeting. So I think there's a problem with tabling at the university. Officially, all lectures are supposed to be face-to-face, but so the Wednesday lecture will be face-to-face. I think that's timetabled across the entire semester. But this Monday slot, I think most of the time will be virtual. So today, yeah, the 26/9/2022, this is our second lecture. It's our third slot. And we started with basics. We'll carry on with basics for analog VLSI design. In particular, we'll look at what we want to do is the amplifiers, but in steps of what we'll cover today, we'll carry on with devices. We had started with the NMOS. So we'll look at the NMOS structure. We introduced this already. The symbol is important, and how we do the biasing. And the device can be used either as a switch or amplifier. For the digital VLSI part, you use the device as a switch. For my part of the course, we use the device as an amplifier. So we'll look at that, and we'll look at how to model. So if we use a maths equation, or if we want to use a computer to capture what the device is doing, we need what we call a model. And the two variations of the model, there's the what's called the large signal, and small signal. So that's quite a lot just for the NMOS device. So once we've looked at that, we'll repeat the same for the PMOS, but not everything. Most important for the PMOS, in case I forget, we'll use this as a reminder. The symbol is important for the PMOS. We need to be able to distinguish between an NMOS and PMOS. The biasing is particularly important. And because when we talk about this, we use the symbol for the device to indicate which device is which and how it's biased. The biasing for the PMOS is distinctly different. It's the same, but it uses reverse polarity compared to the NMOS, and it's important to be clear about that. The modeling is quite identical. So that's number two. And the third thing which we'll do is basic NMOS. Most amplifiers use an NMOS device. I think by the time we finish those three things, the hour will be done. So that's the plan for today. If we go through that quickly, we can always add a fourth item. So picking up from where we left, I had the structure of the NMOS. And as I said, the NMOS device, we make it from a PMOS wafer. I think I'm in the office. Let me just get a wafer to show you. I'll bring it on Wednesday in class. Give me a second. So you've probably seen this. This is a picture of a CMOS wafer, one of the devices we make in Glasgow. So we call it wafer because it's a thin sheet of material. So this thin sheet of silicon, and you make your devices here. Once the devices are made, this is cut up into individual chips and it's packaged. So apologies, I need to put my phone on mute. So the wafer, like what I've just shown, for most technology, the wafer will normally be p-type. So it's not, the material has p-type impurities. So it's conductive, but using a positive charge or holes for conduction. And two regions, we dope them positively. We dope them with an N-type dopant. So electrons are used for conduction in this region. So this region, we also introduce doping, which converts the p-type into N-type. And the little plus says that it's highly doped. If there's no plus, it means that the doping is light or the level of impurities is not very high. With one plus, the level of impurity is quite high. And if you have two pluses there, it means the level of impurity is even higher. And we say this region, we have an oxide layer. So usually this is SiO2. And on top of this, we have metal. And the last thing we did last time was that if we dope a piece of semiconductor, it behaves like a piece of metal. So that means that if we connect a metal there, the two electrically both conduct. So this is our main contact number 2. And here we can connect another piece of metal. And this is our main contact number 1. The main contact number 1, we call it the source. The main contact number 2, we call it the drain. And the central contact, we call it the gate. And the simplest model that I used last time was that this device is like this, where this is main contact number 1, main contact number 2, and main contact number 3, which is the gate. So we have the main contacts, and this middle electrode determines whether we have a connection between a drain and source. This part of the transistor corresponds to this central part, and we call it the channel. These are just the names for the regions of the transistor. This one, we call it the gate for obvious reasons, because it can either close or open the channel, so it's like a gate. And source and drain, in other technologies, they are called the emitter and the collector. So one emits the carriers, or the source, it gives the origin for the carriers, and the drain is where the carriers end up or collect up at. So these names are just descriptions of what the transistor does. So actually this transistor, yeah, so how do we bias it? Normally, if we want a current to go through drain and source, we'll connect a battery between those two points. So if I connect a battery, normally I can connect it like that. So I can connect a battery between drain and source. And I can also connect another battery between the gate and the source. So I use this as the reference electrode, and so I connect a potential between those two. So initially, if this is 0, if I don't have any applied voltage here, and so these voltages, normally we can vary them. So if we start with the gate voltage is at 0, and I connect a positive voltage between the drain and the source. Actually, in that situation, the switch is in this configuration. So the switch is open and no current flows through. And the reason for that, for those of you who've done this before, it's quite clear. This region is N-type. This region is P-type. So we have a PN. This is a PN junction at this point. And that one is also a PN junction. Because the bulk material is P-type and we make this type N, so there's an interface where one side is N, the other side is P. There's an interface where one side is N, the other side is P. And if you know your diode electronics, if we make that positive, then this diode is reverse biased and no current flows through. So when the gate voltage is 0, no current flows through. So the switch is actually open like this. So even though you have a battery across those two, no current flows through. If we increase the voltage of the gate a little bit, still, because this is still reverse bias, no current flows through. But if we increase the gate voltage high enough, this positive voltage, we have electrons in those two regions. So if we increase this positive potential high enough, it will attract the electrons. And when it attracts the electrons, they come and accumulate underneath the, just on the surface, on the silicon, underneath the SiO2 layer. And when that happens, so when the gate voltage is high enough, we can have an accumulation of voltages, accumulation of electrons in this area. And because we have no excess electrons in this area also now behaves like an N-type area. And then we have a path through which the current can flow. So when the gate voltage is high enough and we increase the drain to source voltage, a current will flow through. If we increase the gate voltage even higher, we have more electrons here, and therefore we can carry a much higher current. And so for increasing drain to source voltage, higher currents will flow. So we can control with no voltage at the gate, there's no current flow between the two main electrodes. If the voltage is beyond a certain value, we're able to attract electrons here and current starts to flow. If we increase the voltage at the gate even higher, we attract even more electrons here and more current can flow here. So this device, another name for this device is, it's called anomaly off device. So without the gate voltage applied to a certain positive potential, no current can flow between the two main electrodes, and so the device is normally off. So it's called anomaly off device. Another name which you may be familiar with is it's called an enhancement mode device. In that if we have a voltage at this point, we attract electrons here, so we can enhance the conductivity in this region, and so it's called an enhancement mode device, as opposed to the other devices there, which are called depletion mode devices, but this particular one is called an enhancement mode transistor or anomaly off transistor. Just before Live transcription, the answer is no. You don't need live transcription. It will confuse you more than it helps you, young man or young lady, because it doesn't quite pick up the words properly. And so what it tries, it's better to listen to me carefully and to ask a question if you don't, if you want me to repeat anything. So live transcription is not very useful. So are there any questions or comments before I carry on? So the final thing I say about this transistor before I move on is that the backside of the transistor, we normally introduce another metal contact. And this contact, we call it the body contact. And this contact is normally connected, for the PMOS, it's connected to the source. The reason for the body contact is you want this region to have a defined potential. And if this is, if this bottom side of the wafer sits at the same potential as the source, it means that the PN junction between the body and that end region is always reverse biased. So that means we don't have the transistor current, you want it to flow in this channel region. You don't want it to come outside of the transistor. And by connecting it like this, we ensure that the transistor is nice and isolated here. We don't have currents that that flow towards the bulk of the transistor. It's called the body contact, or sometimes it's also called the bulk contact. So I'll summarize this on the next page. So our NMOS device, if we look at the characteristics, so the current between the two main electrodes, drain to source, we can only have a current as a function of the drain to source voltage. So if we connect a battery between the drain and the source, we can have a current flowing through. As we said, if there's no gate voltage, the current flowing through is 0. For little gate voltages, the current flowing through is still 0. But if the gate voltage, if the gate to source voltage is high enough, then the current will flow through. And this one, the voltage at which the current starts to flow, we have what we call the threshold voltage. So if the gate source voltage is higher than this voltage, then we have a current flowing. And if we increase, so we can call this VGS1. And if we increase the, if VGS2, if we increase the gate voltage, even higher currents can flow. And if we increase that even higher, then even higher currents can flow. At low voltages, for low VDS, IDS is proportional to VDS. So at low drain to source voltages, the current increases linearly with applied voltage. As the applied voltage increases, the current also increases. But after a certain point, so why is the current constant when VDS is increasing? So initially, at for low voltages of VDS, the current increases. The transistor behaves as a resistor, because yeah, remember that's how a transistor looks like. This, we have electrons there. So when drain to source voltage is low, it behaves like a resistor. As you increase drain to source voltage, the current increases. But after some time, the current levels, and the reason for that, the current levels because of the so if I call this V, That's called the knee voltage, where it looks like a knee, where the current flattens out. For VDS greater than V knee, current saturates. So the current saturates, that's the word that's used. So this region, sometimes it's called the saturation region. It's called the saturation region because the current saturates. The more common word that we use is active region. Why the current saturates is one of the reasons is because of physics. Physics, which means if you read the first so many pages, the electrons, when we apply a voltage between drain and source, the electrons start to move. And if you apply more voltage, they move even quickly. So the current increases. Remember, current, if we write it in mathematics, we write it like that. Current is dq dt, or the rate at which charge is changing, or the speed of the electrons, so speed of electrons. So how much current flows depends on how quickly the electrons are moving. And if VDS is slow, the speed is slow, and so the current is slow. When we increase the applied voltage, because we now have higher potential, the electrons move quicker and the current is higher. Yeah, and if we increase even further, the electrons get faster. But just like everything, like even you, if you try to run, you'll reach your top speed. So at this point, the electrons reach the top speed, and even though you continue to apply the voltage, they can't run faster. It's like if you're running 100 meters, you know, you can put in more effort, but there's a high speed that each one of us can go. So the reason why it flattens out is because of the physics. And the other reason why it flattens out, it's explained in the handout. It's more about physics, but there's a condition called pinch-off. And this is explained in the earlier pages. Try to read it, and if I need to explain further, you ask me that. Ask again. Oh, the chap on iPhone, next time connect from your laptop and be somewhere stable. So I don't want to confuse you. We are a class of 160, so the transcription will confuse you even further. So if you can't hear me, you think the computer hears me better, I think you're mistaken. You can listen to the lecture again. This is being recorded, so. So for your digital VLSI, in digital VLSI, you normally, when the transistor is on, it's low voltage across it and high current through. And when the transistor is off, there's no voltage, there's no current through it, and the transistor is off. So for digital VLSI, you're normally switching between those two positions. Either the transistor is on or off, and we use the transistor as a switch. And for analog VLSI, in this position, where the current levels off, even though we are increasing VDS, we are able to use the transistor as an amplifier. That's one of the interesting things about our transistor. The fact that we have current constant and VDS is changing, but current is constant. This enables us to use it as an amplifier, as we'll see. Actually, here we can call this, we can call this a voltage. A transistor is called, we can also call it a voltage controlled current source. So if you know something, for those of you with the EEE electronics background, you know what a current source is. So a current source is, it gives a certain current irrespective of what's connected to it. And here, this transistor, it always gives this current. It doesn't matter what the voltage across this device or what we've connected it to. So it behaves as a voltage controlled current source. And eventually in this region, we can use the transistor as an amplifier. So for analog VLSI, we are using the transistor in this region, while for digital VLSI, you're using the transistor. It's either on, you're either there, or it's off, this no current going through, while for digital, for analog VLSI, we're in this region where the transistor works as a voltage controlled current source. What else do I need to say about this? So the symbol of the transistor is important. So those are the 3 electrodes. This is the drain, this is the source. And because the flow of conventional current, at least in Western Europe and the US, we assume it to be flowing. So the electrons will flow towards the drain because that's the potential. But the current flows from drain to source for this device. So we put a symbol there. Channel length modulation, yeah, that's an advanced concept which we can probably discuss later in the course. I think you'll discuss probably a bit more on the digital VLSI, but probably not useful for me to mention it now. Then the body connection, which I mentioned, normally for the NMOS, will connect it to the source. So actually, when you do your lab, you'll find that your transistor is 4-terminal. For the NMOS, the body will always connect it to the source, and that's the gate. And you have these two lines which correspond to the gate region. You have an insulator there, SiO2, that's the gate, and that's a semiconductor. So this looks like a capacitor. So the symbol for that looks like that. Actually, the inner track is a bit longer. For the PMOS, for the NMOS, the symbol looks like that. And normally, if we are making, so if I use this symbol to get the transistor characteristics, I'll draw it like that. And I would have a voltage between drain and source. And I would have another voltage between gate and source. So this one, I call it VGS, source drain. And this one is, I actually call this VDD and VGG. So this is the gate, the voltage that we use to control whether the transistor is on or off, the gate voltage, and the voltage that's used to determine the current that goes through. And across the transistor, that's gate, I have my voltage VGS there. So in this particular case, the supply voltage is the same as gate to source voltage. And in this particular case, the supply voltage VDD is the same as the transistor voltage. And if we plot them, it looks something like that. So the source terminal is common to both the gate voltage and the drain voltage. And so this configuration, we call it a common source configuration. And you can have other configurations, but other configurations where we want to put the gate the reference or drain the reference, but this is the most common configuration which we should use. So that's the common source configuration of your structure. And we can call this the input port. Actually, I could do like that. So here is my VGS. My transistor is a 2-port network, and this is VDS. And inside here, I have my transistor. So of course, the gate is connected to that, and the source is connected to that, and the drain is connected to that. So the transistor, often we can say, we consider is a two-port network where the input is the connection to the gate and the output is connection to the drain. So as I said, we can use this device as an amplifier or a voltage controlled current source. The control is the gate voltage, as you can see. The gate voltage sets how much current flows. And so the first model of the transistor is I have the gate. Normally, we don't have any current flowing between the gate and the source because we have an insulator between the two. So I can just leave that as an open circuit. And between the drain and the source, I can use a current source symbol and I can call that current VDS. And this is my drain, this is my source, and this is my gate. This is my source, this is my gate. So the first model for the transistor, we can represent it as a two-port network where we have IDS, and IDS depends on VGS. It depends a little bit on VDS, but it mainly depends on VGS. So the current flowing through, so we have VGS there. The current flowing through between drain and source depends mainly on VGS, a little bit on VDS, especially in the linear region, in the region before the knee voltage, before it flattens out, it depends a little bit on VDS. But after that, it just depends on VGS. So that will be the first model of the transistor, and we call this a large signal model. Large signal model, or you can also call it a DC model. A large signal for AC, but you can also call it you can call it a DC model. So we look at so at this point in time, we should all be familiar with the structure of the NMOS. We should know its symbol. We should know how it's biased and when it's used as a switch or as an amplifier. And we know something about its large signal model. It's a math equation that represents the current. It's a two-port stuff. What we haven't done is the small signal model, and we'll do that after I've looked at the PMOS device. Okay? So just be sure, if you're not happy with any of those things with the text, please do ask. Because the rest of the course will go a bit quicker, but if you're happy with these things, you'll be able to follow the rest of the slightly more advanced stuff. For the PMOS device, we would make both all devices on the same wafer. So we also start with a P-type silicon substrate. But because it's a PMOS device, actually, we make a large area N-type. So we convert a large area into an N-type region. And the reason for that, many of you would understand, but if you don't, in time, you'll get the hang of it. And then I make this region P+, I make this region P+. And just like in an NMOS device, I make this region, I put an SiO2 insulator there, and here I put my gate electrode. So I have metal there, and this is my gate. And actually, because it's a PMOS, this particular electrode, I'll call it the source, because we're using positive charge to carry electricity in this particular device. Yeah, everything is a little bit reversed, and this one I'd call it the drain. This particular, you'll do this in in the digital VLSI, but it's in your handout. This region, which we make, where we make a PMOS device, we call it an N well, or an N region. So this is the N silicon. We make an N region within the P silicon substrate, because the substrate that we start off with is P-type, but we want to make an NMOS device. The NMOS device uses holes, so we need this to be P-type, because eventually we want to attract holes here, and they connect the two main electrodes for the current to flow. So the way we bias this, just before I draw the bias, I'll ask a little question to the class. Please answer, either unmute and answer, or type the answer in the chat. What kind of potential do we need at the gate to be able to attract the carriers here to fill up this channel region?
Negative.
So we need negative potential here. Because these are positive carriers, we need negative potential. If you don't agree with that, please say. So while in an NMOS device, we needed positive potential, here we need negative potential. So I draw this like that. So the negative potential is connected to the gate. If this is negative, we are able to attract the holes from both there and there to come in this region. And so actually the drain, we use negative voltages, excuse me. So I use still my source as my reference. And I use negative potential there. Once electrons, just like in the PMOS device, if the negative potential is not high enough, you're not able to attract the holes which are here into this region, so no current flows. So this device in terms of the switch action, I have my D there, and I have my S there, and I have my gate at that point. And so before you apply your negative potential to the gate, the switch is also open. So it's a normally off device, also this configuration. And you only turn on the device, or you close the switch if you put large enough negative potential here. So the threshold voltage for this device is a negative number, it's a negative potential. And once VGS is greater than the threshold voltage in terms of magnitude, we attract holes here. And so if we vary the drain to source voltage, the current flows across this device. And in terms of, if I have, what's the symbol for the device? The symbol is nearly identical to the symbol for the NMOS. And actually, I'll put the source at the top. You'll understand the reason for that in a second. And I put the source at the bottom, the drain at the bottom. And also, we can also have a body electrode. Actually, the body is somewhere here. Normally, I should have drawn this in a better way. The body is also connected to the source, and that's my gate. And the reason for me to draw it like this is I think I've drawn that wrongly. No, I think I'm okay. We need a negative potential there. So this is like this. Yeah, that drawing is a little bit all over the place, but it gives you a chance to think through this. So I need a negative voltage between the gate and the source to turn on my transistor, and I need because we're using holes, I need reverse polarity. So if I put excuse me, I think I'll just redo that. Excuse me, I'll just redo that. drain, and this is the gate. So between the gate and the drain, we need a negative. So between the gate and the source, we need a negative potential. So if I put that like that, that's negative, and this one, if I do like that, that's negative. Yeah, that's correct, but it doesn't make my point very clear. Just I'll draw a similar symbol just alongside. So if I made this the source electrode, this the drain electrode, and this the gate electrode, then I need negative potential between the gate and the source electrode, and I need negative potential between the drain and the source electrode. So yeah, so if I drew, I could draw the symbol like this, where this is the source, this is the drain, and the arrow here, which shows the direction of current flow, because that arrow is normally connected to the source lead, because we are using holes for conduction. So the current flow is opposite to the electron flow in a PMOS. So the arrow is towards the device. So it's like that. And if I use the symbol where the drain, source, and gate are in the same places as for a PMOS device, then I need a negative. So I have my negative potential here and positive potential at the bottom, negative potential, positive potential there. Often in the circuit, we only have one battery supply, and the battery supply is that and that. So that's my positive and that's my negative. So the PMOS devices, we would normally, so instead of doing like this, which is correct, we flip them around so that the source is on top. So this comes on top, the drain is at the bottom, the gate remains in the same place. So this battery, the positive potential is on top, negative potential is this, but because we flip the device around, the gate to source voltage, because gate is at a lower potential compared to the source, the gate to source potential is negative. So by flipping the device around, I can use my source, just like for the NMOS device, and it will have, even though this is positive on top and this is negative at the bottom, the control voltage to my PMOS device is negative. That's quite important when you draw your circuitry, because you will know, even though you only have one positive supply in the device, this positive supply can supply your NMOS in the normal configuration, but the PMOS device will normally be flipped the other way around so that the source electrode is in the wrong position compared to the drain electrode. But that way, we have the correct potential to turn the transistor on. So just to recap, so this is also a voltage controlled current source, as it were. Let's draw the diode the characteristics of this. So this is IDS, the current is negative, so I draw it like that. And the voltage which we apply is negative, and the current through this is VGS1. The current through the PMOS device would flow in the negative direction. So this is some more negative potential to that. So in terms of magnitudes, probably better to write them like that. So this is a more negative potential, You have more current flowing, but it flows in the opposite direction to that of an NMOS device. But often, like in an inverter, you're probably looking at the inverter in your digital VLSI part. These two devices are connected in series. So that's why, even though the currents flow seem to be flowing in the opposite direction, by flipping this device upside down, we get all the currents flowing in the same direction. So just to recap that, could you tell me if you've looked at the inverter already in your digital VLSI lectures? Have you looked at the inverter in your digital VLSI lectures? Yes? Someone says no, someone says yes. So the inverter, the digital inverter looks like this. If you haven't done it, you'll do it on Friday. Anyway, I'll draw for you, and just to illustrate the importance of the symbols. Oh, no. So have you looked at that circuit in your digital VLSI? This circuit is called an inverter. By looking at, this is your PMOS device. This is your NMOS device. And the arrows tell you that the currents flow in the same direction. And if this is low, this is high. If this is high, this is low. You'll do this in digital VLSI. But actually, so in analog VLSI, so analog. In analog VLSI, I would draw the circuit like this. And my source for the PMOS is connected to higher potential. The gate is at lower potential. My control voltage is a negative voltage here. For the PMOS device, the source is always connected to the lower potential. The gate will be at higher potential. My control voltage here is always positive. So if I draw this in analog VLSI, I'll always use this particular two symbols. The same circuit when my colleague Steve Toms will draw it for digital VLSI, it will probably look like this. It will probably look like this. So another symbol for the PMOS device is this. So this is your PMOS device. This is your NMOS device. So there is no arrow there to show direction of flow. The only thing that tells you this is a PMOS device is the little blob here. And as I said, the PMOS devices, our source, we flip the device the other way around, such that the source is at high potential because that gives us the negative control voltage. So in the digital VLSI, this circuit, you're likely to draw it like that. But if you draw it like that, always be aware that actually for the PMOS device, your source is there. Your source is there, your drain is there, your gate is still there. But for your NMOS device, your drain is always at the top, the source is always at the bottom, and the gate is always at the same place. So I think so much for today. We start with amplifier work in the face-to-face class on Wednesday, but we'll build on that. That's the basics we need to be able to do the amplifiers now. Okay, we'll see you on Wednesday in the face-to-face class. Cheerio. Unless you have a question, have another 2 minutes to hang around to answer any questions you may have.
Thank you for the lecture. Can you just briefly explain how you know the PMOS and the NMOS from the arrow direction?
So in analog VLSI circuits, we'll always be very explicit which device is which. So the PMOS will always have an arrow into the device, while the NMOS, the source arrow, the source will always have an arrow to it, and for the NMOS, the arrow is out of the device, while for the PMOS, the arrow is into the device. In the digital VLSI, this is both textbooks. In the digital VLSI, they don't give this much detail because it's digital VLSI, it's only ones and zeros. When we do amplify, it's a little bit more complicated than that. So in the digital VLSI, the PMOS device, you know it by, you will have a little circle on the gate. So it tells you this is a PMOS device, but you should always know that because a PMOS device, your source is actually the higher electrode and your drain is the lower electrode. While the NMOS is almost exactly like, the drain is the high electrode and the source is the low electrode. So you know that's a PMOS by the blob on the gate electrode. There's a little circle there that tells you that is a PMOS device.
Oh, okay. So on the analog side, you don't actually flip the device. You keep it the same orientation.
No, on the analog side, we flip in both technologies, we flip the device.
Okay.
So if you look at where my G, so drain and source, drain will always be up and source down for the NMOS device. But the PMOS device will always be flipped because like VDD, we only have one battery. And this one battery supplies positive potential. It supplies positive potential to the NMOS device, and it supplies negative potential to the PMOS device. So for that reason, the PMOS device is always flipped. The source is always connected, it's always the top electrode, and the drain is always the bottom electrode. So that's not always clear in the digital VLSI circuits, and but just beware of that. Just beware that in the circuits, the NMOS device, the source will always be the higher terminal, while the drain will be the low, while the NMOS devices are it's like we do.
Okay, thank you.
Okay, no problem. Okay, see you guys on Wednesday.